Now we will solve example 2.7, and this example we have solved in the previous example in another way, and now here we will solve it with a different way. So let me recite the example. You are seeing it on the screen as well. Find the potential of a uniformly charged spherical shell of radius r is shown in figure. So let me draw the figure, and the sphere is like the previous. We are having a sphere of radius r. Okay. This is the center of the sphere, and this is any portion on the surface of the sphere. So its distance from here is r. This is towards the surface of the sphere, and let me draw the axes as well here, like here and here. So this is our x-axis, this is our y-axis, and this is the z-axis. And here we have this length, which is here, is equal, this angle is, this length is equal to z here, and the angle here is theta prime, while from this source, this is the source, and from here means there is charge, sigma charge on the surface of the sphere. It's a surface charge on the sphere. So I'm selecting a fraction of it, and this is our observation point P here. So this is from here to here, and this distance is tilted r here. So we are having capital R here, and we are having here the tilted R, and here the Z. Now we will use the relation which we use for the continuous charge distribution. For example, this V of R can be written, and we have written it in terms of Q. So if I want to write it in terms of the line charge, then I will have this thing is 1/4 pi epsilon naught, and this is Q over this. So I can write this thing is lambda dl prime over tilted r. And this is the same if we write is 1/4 pi epsilon naught and integral lambda dl prime over tilted r. Or this is for a surface charge 1/4 pi epsilon naught and sigma dA prime over tilted r. Or in volume terms, I can write 1/4 pi epsilon naught, and this is rho d tau prime over tilted r. Just like we wrote the same thing for the electric field, but here was r square in all of them, and here we are having tilted r. We can use the law of cosines, as we have derived this one in chapter first in vector analysis. In one of the example, we have derived that if this is the length that I am finding out, and this is theta prime between the two lengths z and r, then I can write this tilted r square equal to z square, the r square plus z square minus 2rz cos of the angle. So this is law of cosine. We have already derived this one, and now in terms of this I will write is we are dealing with this one, the V of R here, sigma dA prime. So I will write this thing is V of, now the point R is actually V of Z, because our observation point is here on the Z axis. This is point P. So V of Z equals 1 over 4 pi epsilon naught and integral, and I will write the sigma dA prime over tilted R. So this is equal to 1 over 4 pi epsilon naught, and sigma will come outside because it is constant. It is not supposed to be integrated here. It's a constant on the surface of this sphere, spherical shell. And then for dA, I can write the length, the area element. This is R, and I will write this is R square because there is no integration on R, and sine theta prime, d theta prime, and d phi prime. The area element we have already derived in spherical polar coordinates. Divide by tilted R, so R will come out to be the square root of this. So R square plus Z square minus 2RZ cos of the angle, and this is in square root. So we have derived the V of Z. Now in order to write it in more simple form, let's multiply it here. So 4 pi epsilon naught V of Z is equal to what this will be, R square. There is no integration on this one, so sigma R square will come here, sigma R square, and then when we will do on a spherical polar coordinates, d pi will give us 2 pi. We know this thing. So here is 2 pi sigma or R square, and then I can write this one. If I move it up, then it will be integral and R square plus Z square minus 2RZ cos of the angle between R and Z power minus 1 over 2, and then sine theta prime d theta prime. So this is our integration. We will have to solve this integral. Now I know one thing, that when we have an integral like here x to the power n, and in front of it is its derivative dx, means x to the power, and then the x is having its derivative in front of it, then this is equal to x to the power n plus 1 by n plus 1 here. And if there will be some different variables here associated with this one, then we will write them just below it here with this one. So this is equal. Now if I look here, this thing is equal to, if I look here, what's the derivative of cos theta? The derivative of cos theta prime is equal to minus sine theta and prime d theta prime. So it means this one has this derivative. So the derivative is here, but there are two additional terms here, which means the minus is with this one. So minus cos theta will have this thing, minus cos theta will have this thing equal to plus, so plus sine theta. While what about this one? This will give minus, what about the 2RZ? So if I divide this by 2RZ here, then this will come here as well. So minus sine theta this into RZ will be with this. So I can write that the integral of this one, and similarly, what about the minus power? The minus power will come out to be that it will be minus, like the power of this, minus half plus 1 and whole divided by minus half plus 1. So this will be 1 over 2, because this 2 and 2 minus 1, 1 and 1 over 2, and here this will also become 1 over 2. When this 1 over 2 will go up, then it will cancel with this 2 and we will have only RZ in the denominator. So the integral will come out to be that 4 pi epsilon naught V of Z equals to and we are also having the theta value from 0 to pi. So this implies that this thing is actually equal, 4 pi epsilon naught is equal to 2 pi sigma r square, and then 1 over RZ here, 1 over RZ here, and then this integral, and it will be the square root of this one. So this is r square plus z square minus 2rz cos of theta, and this is theta prime. So this ranges, it's having a square root. So this is ranging from 0 to pi. Now R here simplifies with this one and 1 R remains, and we will have this thing equal to 2 pi sigma R over Z here, and then we will put the values. When I will put cos theta equals to pi, this theta equal to pi, then cos pi is minus 1 and this will become plus. So this is r square plus z square plus 2rz, and this is a square root of it, minus, when cos theta is 0, then it is 1, so it is equal to r square plus z square minus 2rz, and this is square root, and we are having the square brackets here. This thing is further equal to 2 pi sigma r and divide by z. This thing I can write that this is r plus z whole squared and square root minus r minus z and whole square root. This thing is equal to this, and this is equal to, finally we will get this thing. Now here is, we are related to two things. The two things are that we will find the field outside and inside. So for outside, we know that for outside of the sphere, we will have z to be greater than r. Like here, this is z, the z-axis, z is supposed to be greater than r, the radius of the sphere, so we will be outside the sphere. And when we are inside the sphere, then z will be less than r here. So keep the values here. This is r plus z whole square. Whether z is less or more than r, it doesn't matter here. But here we will have to be careful that this thing, the r minus z whole square, is also equal to z minus r whole square. There is no difference at all here. But when we will be considering this thing for outside the sphere, we will prefer this relation, because here z is to be greater than r in order to keep this value positive. We will not write it like this, otherwise they are the same and we will have to differentiate this thing. So for outside the sphere, when z is greater than r, outside the sphere, then z is greater than r, and we will have to keep that thing in mind. Another thing, there is some simplification on both sides. This is 2 pi, and 2 pi is going with this one, only 2 remains here. And epsilon naught is there, sigma is there, so we will have v of r, which is actually v of z here with us. V at point z is equal, here 2 epsilon naught will come down here, so we will have sigma r over 2 epsilon naught z here, and then here is we are here, so this is r plus z here and minus. Now keep that thing in mind, we are outside the sphere, so this is z minus r, and this will give us, look here, this z is cancelling with the z, and minus r becomes plus r, so it becomes 2r. 2 is cancelling here, and we are having sigma r square over epsilon naught z. Sigma r squared over epsilon naught z here for z greater than r. Similarly, when we are inside the sphere, for the inside of sphere, z is less than r. So I will write now this thing, v of z equals sigma r over 2 epsilon naught, and now here this is r plus z minus, now we don't care because r minus z or z minus r, so this is r minus z, now r is greater than z, so it is to be positive, and I will write r minus z here, and then this thing is equal to the r and r are cancelling with each other, and z will remain as 2z, 2 will cancel with this one, and we will have sigma r z divided by, and here only epsilon naught will remain because 2 will cancel with this. So we have, okay, one thing, here we are having z as well, so this z will be cancelled as well for this thing, z less than r. Now we have to see dimensionally that we are right, because I know from here that what is this thing, sigma. Sigma is charge per unit area. Now charge in area is area of the sphere. So this is 4 pi epsilon naught r square. So we will have charge per unit area 4 pi epsilon naught 4 pi r square. So this I can simplify here. Let me write it here, that v of z for z greater than r is equal to sigma r square over epsilon naught z. Now this thing is equal to sigma is charge per unit area, and epsilon naught z, and charge per unit area is 4 pi r squared. So there are some cancellations. This r square goes with r square, and we got 1 over 4 pi epsilon naught q over z here, which is the same as we were having earlier, q over r, because there the distance we were counting is r. And here when I write v of z for z less than r, then this is equal to sigma r over epsilon naught. So this is q over 4 pi r squared, and this is r over epsilon naught. So this is equal, there is one cancellation of r, so 1 r will remain, and we will have 1 over 4 pi epsilon naught, and then q over r, and this is the field which is a constant field inside the sphere. When I go inside the sphere, the potential is constant. For field outside the sphere, it is decreasing as 1 over r. And this is also having the same plot and the same reasoning behind this one. We calculated it in a completely different manner with the help of law of cosines. So this is the solution of example 2.7.